All right, welcome to your first lesson on analyzing two-dimensional collisions using the law of conservation of momentum. Take a moment to look at the objectives of this section of the unit, and then I will give you an example of an analysis of a collision in two dimensions. For our purposes of just getting started, I'm going to use a example that doesn't require a whole bunch of math. I'm going to have you imagine two objects. Let's say a blue object I'll draw here that has a momentum because of its mass and velocity of 2.0 kilograms times meters per second. My blue object is going to have a collision with a red object that I'll draw here such that they kind of go off at different angles. You can imagine it this way. Here's my blue object and travel along, hit my red object. The blue object's going to go up this way. My red object's going to, I anticipate, going to go down and to the right. So this diagram represents my before the collision picture. I'll just slide it off to the left here. Put a little line. I'm going to draw my post-collision picture. It's going to look a little something like this. My blue object hits such that it moves off at an angle this way. We'll say it has a momentum of, let's say, 1.0 kilograms times meters per second. And my red object is going to travel off in this direction at some unknown momentum. Now, we've just finished studying linear collisions, so many people might say, well, this is pretty straightforward. It's the law of conservation of momentum. We started with an initial momentum of 2 kilograms meters per second. After the collision, our blue object has 1 kilogram times meters per second worth of momentum. And so it's pretty obvious, right? This red object must have 1.0 kilograms times meters per second worth of momentum. Since 1 plus 1 adds up to 2, law of conservation of momentum just tells us that that's the obvious answer. However, we can't lose sight of the fact that momentums are vector quantities. We don't simply add the magnitudes together unless it makes sense to. In this case, we have to consider that the 1 kilogram meter per second displayed by the blue object after the collision is not directly to the right anymore. It's kind of to the right, but it's kind of up. The blue object's kind of going down, it's kind of going to the right. So we need to analyze this as a vector problem as we would with any vector quantity. So let's get rid of this 1 kilogram meter per second, and I think I can convince you that it is indeed going to be something different than 1 kilogram meter per second in that direction. It's not that we don't use the law of conservation of momentum. We can certainly still say that the sum of all momentums before the collision has got to be equal to the sum of all collision or all momentums after the collision. So we're still going to apply the law of conservation of momentum. We're just going to continually remind ourselves that these are vector quantities. If I were to draw what this formula tells me I should be doing, it would look like this. This formula says that when I put together my initial momentum of the blue object before the collision, which was 2.0 kilograms times meters per second, add to that the initial momentum of the red object, which was just 0, so I'll put a dot there. So 2 kilogram meter per second to the right and 0 kilogram meters per second in no direction should be equal to the vectors that we have after the collision. In other words, the blue vector, which is going this way, and the red vector, which is going this way, added tip to tail, as we do with vectors, should add up to be the same as the initial momentum of the blue vector and red vector before the collision. We will need one more piece of information, and that is at what angle was one of the objects moving after the collision. I want to give you that right here. We'll say that the blue object was moving up at an angle of, let's say, 30 degrees from its original direction. So on our diagram down here, we could label this direction as 30 degrees. This momentum of 1.0 kilograms times meters per second. And so 1 kilogram meter per second at an angle of 30 degrees added to the red vector's magnitude and direction should add up to the original momentum. That's our 2 kilograms times meters per second. So we can label this 2.0 kilograms times meters per second to the right, because that's how much momentum we had to start with. So now we have a triangle in which we can start to analyze the components and make sure that before and after the collision they do add up. Now, it's not necessarily going to be the case, but for our discussion, again, I'll give you one other piece of information, and that is that the red object moves at an angle equal to 60 degrees from directly right. That way we have a nice right angle triangle here where this angle is 60 degrees. You can convince yourself then that this interior angle here is indeed 90 degrees. So at this point, you really have two things you can do. You could draw a nice scale diagram, but most people are comfortable enough with the math that they like to revert to trigonometry. So we have a right angle triangle with one of our sides being 2 kilograms times meter per second, one of our sides being 1 kilogram meter per second, and it's a right angle. So I think we have enough information now to find out the magnitude of the red vector. So the magnitude of the red vector can be solved using Pythagorean theorem. A squared plus b squared is equal to c squared. We know the hypotenuse and we know one of the sides. So let's say A is 1.0. I'll leave the units off for now. 1.0 squared. B is going to be our red object's momentum vector. And C is going to be our hypotenuse. On our picture, it's our 2.0 kilograms times meters per second squared. All right, so do our math. 1 squared plus b squared is equal to 4 squared. B squared must be equal to 4 squared, which is 16, minus 1 squared, which is 1. So 16 minus 1 is 15. So b is equal to the square root of 15. Pull out your calculator, you find that to be 3.87, which we'll write as 3.9 kilograms times meters per second worth of momentum. So going back to our vector diagram, if this is 2 kilogram meters per second, this is 1, now we figured out that this side is 3.9 kilograms times meters per second at an angle of 60 degrees down from the original position, 60 degrees. Going back to our original picture seems consistent. We had our object coming in at 2 kilograms meters per second, strikes the red object, which now goes down at 3.9 kilograms times meters per second. Blue object goes up at 1 kilogram meters per second, seemingly defying the law of conservation of momentum if you only consider the magnitudes of the vectors. But again, momentum, it's a vector quantity. This is okay, 3.9 and 1 after the collision, even when we only had 2 units of momentum before the collision, is all right because of the vector nature of things. Next lesson, we'll take a look at how we can make this, I guess, a little more interesting if rather than starting with the momentums, we start with masses and velocities.